everyone. So today we're going to be going over a problem involving the rules of inference. So it falls under discrete math or logic class or philosophy. And these are the rules of inference right here that you typically see out of a textbook. So we have addition, modus ponens, modus tollens. We won't be using every one of these right here today, but I just wanted to list them out. These are the usual suspects, as you can say here. And let's look at the problem we'll be working with today. So we have a couple statements here. Everyone in New Jersey lives within 50 miles of the ocean, statement one. And then the second statement is someone in New Jersey has never seen the ocean. What conclusions can be made, if any, using rules of inference? Right. So we want to use those rules that we previously looked at to make a conclusion. Now, if you looked at those rules, you saw P's and Q's, ands, ifs. You want to basically write out your statements in that format, basically, here in that predicate language. So first thing we have is statement was everyone in New Jersey lives within 50 miles of the ocean. So I'm going to make two statements here. J of x lives in New Jersey, and S of x lives within 50 miles of the ocean. X is just some person here. It's an element of the universal discourse, as we like to say. So how do I write an expression involving quantifiers and predicate logic here? So the way this is going to work is as follows. So the word everybody lives is like for all x is another way of thinking about this. So for all x, and yeah, we're told that if you live in New Jersey, then you live within 50 miles of the ocean. That's another way of saying that statement. So I'm using an if-then here. Okay. All right, so then what we're going to do next is this. We're going to look at the next statement when someone in New Jersey has never seen the ocean. I'm going to include this statement, O of x, which is x has seen the ocean. And how do I write this in with quantifiers? Well, the word someone means there exists some person. So first of all, they live in New Jersey. So this, you would have to have that J of x has to be true and not O of x, because that person has not seen the ocean. So we're negating the statement O of x. And yeah, for this statement, the statement to be true, the word someone in New Jersey has never seen the ocean, it has to be both the fact that someone lives in New Jersey has to be true and they've never seen the ocean. So that's why it's an and here. All right, so what we're going to do now is take these two statements here, and we're going to use those rules. And let me start with that first statement. That's, the second statement we've made. J of x and not O of x. So this was given to us. And yeah, typically we will write a reason next to it, and then, oops, I forgot. I'm going to put the number 1 here because I'm going to be referencing numbers here. All right, so we're given that statement, and yeah, we typically begin with any information that's given, and sometimes we look at our rules to take a look at, we can say anything here. So if you notice, we have a there exist in that statement we're just looking at. And there's an existential instantiation rule of inference here, which says for all x, P of x, P of c for some element c, therefore P of c for some element c. And basically what that means is that if you say a statement holds, there exists something, someone for which a statement is true, there's someone specific for which that holds. So that's why we're saying P of c for some element c. So we can use that here. And the way that would work is I would say 2 J of c and not O of c. And I'm going to give a reason here, which was existential instantiation on 1. Okay. All right. So we have that statement. What else can we say here? Well, since J of c and O of C is a true statement. So when you have an and statement that's true, both J and C and O of C has to be true. And that's actually a rule of inference. Okay, that is what we call a, sorry, go over here. We have a simplification here. Okay, so yeah, so if P and Q is true, therefore, the rule says therefore P is true, but it can also be Q. Okay, it just says that, yeah, if you give me a true statement, an and statement is true, then both premises have to be true here. So then I'm going to say that J of C is true, and that's going to be by simplification on 2, and then for not O of C is also true, and that again is by simplification on 2. Okay, so we have that. And yeah, often people ask me, well, how do I know not to start by writing both of the things that are given? You just started with one of the statements, you need to write the other one. I could have also written the other statement down, which was over here, the for all x j of x. I could have included that there. But there's no like one rule for this. I just wrote like whatever I saw first. And then I said to myself, well, any statements that I can make that follow from my rules of inference, and if you see any, then you can go ahead and use them, not a problem. But now I will use the statement that was given, which was for all x, the first statement, j of x implies s of x. And what can I say with that? Well, I can say the following, that j of c implies s of c, and that is what we call a universal instantiation. And I'm sorry, I'm going to mispronounce that like all the time. And just so we can look at the rule of inference, it's right here. Okay. So yeah, so if you tell me that a statement holds for everything, then it holds for a specific thing, is what a universal instantiation is saying. Okay. All right. So now what can we do with that and any one of our rules? Well, I notice that you have j of c here is true, and 6 is true, and what you conclude here, again by looking at our rules, I would say that rule modus ponens involved. So if P and Q is true and P is true, then it implies Q is true. Okay, so we have that going on. We have an if-then that's true. We have the premise is true, and therefore we can conclude that the conclusion is true here. So 7, I'm going to say that S of C is true by modus ponens on 3 and 6. Yeah, and I'm just writing down which numbers I'm applying the rule of inference to. And then, well, here's the thing. You have S of C here and O of C is true. You have these statements are true. So you can make a conjunction. So yeah, so if you have two statements that are true and you put an and, that is true, and that is a rule of inference. That is conjunction over here. Then I'll be going back down. And then we have one more thing that we'll do. And I'll just state my reasoning though right now. Conjunction on 7 and 4 and 7. And last but not least is as follows, number 9. There must exist something for which S of x and not O of x is true. And that is an example of this last rule of inference, which says P of C for some element C is true, therefore it's equivalent to saying there exists X P of X. Yeah, so if you told me there's a statement holds for a specific element, then there has to exist some element for which that statement is true, is what we're saying in so many words. Okay, and this is what we call existential generalization. So existential generalization. I misspelled that, but oh well. Doing math, not English here. And then finally, yeah, so we're done. And I could say the following in English. So on actually 8 here, I could say the following, that there exists someone who lives 50 miles from shore and has never seen the ocean. And there you go. So that's what we can conclude. And often people tell me, well, I have to actually use the rules here to make these kind of conclusions. No, you don't. I mean, but I guess you can say, in quote unquote, in everyday English, you're logically saying something using the rules. So there is some reasoning, quote unquote, behind it. Put it that way. All right. Well, I hope that helped. Thank you for your time.